Hello, we are Team APD, and I'm Kim Gyumin, the presenter of APD. We were in charge of the drone team in the integrated autonomous system of vehicle and drone for disaster prevention project. Disaster occurs everywhere, such as mountains, seas, and downtown areas. Among them, we focus on disaster that occurs in areas where GPS is not perfect, such as tunnels, downtown areas, and dense forests. We also focus on implementing the interaction between vehicles and drones. From the drone's point of view, the operation of GPS has a great influence on its movement. In this 2023 first semester project, we studied about preventing disasters using drones and vehicles in places where GPS does not work well. So, our goals are first, drone control without GPS. Second, implementation of drone landing. Third, multi-sensor fusion for localization. To reach the goal, we approached it as a way of designing a drone system, late fusion for EWB, and camera and path planning and tracking. It is essential for drones to land on vehicles in a cooperate system between autonomous drones and vehicles. We land drones on vehicles by creating tracking paths with a synchronous system in real time. Next, drone control accuracy is reduced in an environment where GPS does not work smoothly. We solve this problem with accurate localization of EWBs and cameras using camera filters. First, system. The process works by communicating between the flight controller and the companion computer. The drone is localized through the external sensor, EWB, and camera. And camera filter and trajectory generator operate every time step. The calculated information is handled over the FC and drone is initiated. The motor was controlled by PID control, and the low pitch yaw was mainly tuned. The drone was suspended from the rope and tuned, and the outdoor flight was successful. Second, I'll tell you about late fusion for EWB and camera. The EWB is a sensor that obtains the distance value between anchor and peg. The raw sensor has noise, therefore, we remove the noise through filtering. Based on the Euclidean distance, solve least square to calculate the coordinates of the current drone. Right picture shows the localization results of filtering and non-filtering. We also use cameras to calculate the localization of drone. When marker is detected, we correct the error of UWB using a camera and find the location to land. For accurate calculation using camera, we have to calibrate the camera. Using the calibrate camera, we can detect the marker so drone can land. Camera filter was used to integrate these two sensors when the filter operates. It extracted the drone pose and the covariance matrix of the camera and UWB at each step, and creates a weight matrix based on the covariance matrix. Then calculate the final pose by calculating the localization result of each sensor. Last is path planning and tracking. The best path can be obtained using the following formula, and we apply it to drones. After developing algorithm, we conducted experiments in off-board mode. Localization and path planning had no major problems compared to algorithm. However, there have been repeated cases of landing without landing without maintaining altitude for several reasons. Analyzing the results of experiments, we think the problem occurred because it was out of balance with an inappropriate payload. This problem is expected to be solved by using drone with the right payload and by using more sophisticated hardware. Our plans for next semester are as follows. First, we will change the drone hardware. Second, we will add a new sensor like LiDAR. Third, we will implement other algorithms. Fourth, we will develop path generation and tracking to land drone on moving vehicles. This is the end of our presentation. Thank you for listening.
Okay.